Okay, I think I have recorded this. All right, let's start. So the slope field, or called the direction field. Okay. Now, what's the big idea behind this? Well, why we need this direction field? Okay. This direction field is actually to give us a sense on how the solution curve will look like. Okay. At least we can have some solutions that we can draw on uh, our curve. Okay, let me give you an example. Okay, wait, where is the slope? Okay, this is slope field. Okay, so first let me write some notes. Okay, so the ideas. So first derivative represents slopes, right? So dy dx. This means we have a formula to find slopes that is our gradient, right? Our slope of the tangent line at certain point, let's say xy, point xy, by plug in, plug plugging into dy dx, or maybe let me write in green, dy dx equal y. So what's the deal? The process is graphing the whole line segments of slope at points xy on xy axis, or xy plane, or x-axis. Okay. Okay, and then given specific point that we want to observe, or we can say that's initial condition, then we can find approximate curve whose slopes fit as a solution. Okay. Now probably you might think a little bit, a lot of words here, but the idea basically is, let me give you idea what that is, what this means. Okay. Okay. Example. Okay, let me just go through example. Okay, let me write my equations. X plus y. Okay. Now let's make a table. Well, you can make like regular table, but what I would like to make is uh, this will be, let's say this is x, this is y, and I will have several row and columns. make a little bit longer. Okay, let's say this is start with this is xy, so maybe we start with negative sorry, negative 3, negative 2, negative 1, 0, 1, 2, 3. Maybe too much, maybe this. And this will be negative 3, negative 2, negative 1, 0, 1, 2, 3. Now let's fill in the table with the slope that we get from x plus y. Okay. So for example, we start from negative 2, negative 3, which means this is the point at negative 3, negative 3. Okay. So this point is negative 3, negative 3 will be negative 6, right? Okay, negative 6. So we can write down, let me erase this. So negative 6, okay? So x plus y, okay? So this will be negative 5, negative 4, negative 3, negative 2, negative 1, 0. And same way, we take this x plus y, so negative 5, negative 4, negative 3, okay? And then this will be negative 4, 3, negative 2, and negative 1 is 0, and then this will be 1, right? And similarly, we fill in all this, because it's just x plus y, it's easy to compute, right? But let me just compute this for you. Okay, now we have completed the table. And what we are going to do next is we plot, or we make the small slopes at each point. Okay? The idea of the slope fields is, it seems simple, but you will see that we are going to need, and it will be very important if you can later rewrite some in the last part of our course. Later we will deal with factors, and the factors also can be rewrite in terms of a factor field. So it's similar with the slope field or direction field. Okay, but let me just focus on this one first. Okay, so let's take 1, 2, 3, 1, 2, 3, 1, 2, 3. Okay, and we start. Let's say uh, we start from the slope that is 0. It's easy to draw, right? The just horizontal line. So start from 3, negative 3. So 3, negative 3 is here, right? It's going here, it's going here. This point. So we will have this line here. Okay. And let me erase the here. Okay, this is slope fields for 0, 0. Negative 3, 3, negative 3. Okay. And then 2, negative 2. It's going to be here. And it's going to be here. It's going to be here. Around here. Okay. So all complete. And let's say we have the another easy one is 1 and negative 1, right? So we can start from here, this one. So 3 and negative 2. So we can start from there. 3, negative 2. Okay. So 3, negative 2. So this is 3, negative 2 is around here. And this will be positive, right? Positive 1. So maybe around that gradient. Okay. This is just my approximations. Okay. And then 2, negative 1 around here. And then 1, 0. And then 0, 1. Okay. And then we can also make the negative 1. So we can take the negative 1. So we can take negative 3 to 2. It's around here. It's going to be going over there. It's going to be over there. It's going to be over there. So the idea is just plot all these small line segments, or we call this is the linear element. And if you continue, you will see that the next point that you have, you are going to be like this, right? It's going to be negative 2. And the other one is going to be equal to 2. So here is going to be like that, going a little bit higher like that, increasing in terms of the gradient. Okay. And here it's going to be higher than before. This is going to be higher, really high. And this is, if you continue, going to decrease. Okay. Now, if you try to imagine how it looks like, you can continue this part. Okay. This is also, but let me just stop here for a while. And what does this means? Okay. So let's say we have at 0, 0, we can have these initial conditions, right? And at 0, 0, as we know, that is the dy dx is equal to 0, okay? In which we can see that this red line here. Now, according to what we have in the slope fields, we can argue, or we can make some arguments that one solution that's possible at this initial condition, at this 0, 0, is going to be through here. So probably going to be like that. Okay, probably, right? And then if, for example, we have another let's say the easy one is the gradient 0. So let's say at negative 2, 2. Okay, so this is also dy dx is equal to 0. Negative 2, 2 is here. This is also, we can take this as maybe around here. We can make an argument that that's also our solutions. Or maybe if we take y4 equal 1, which means that we have 4, 1, dy dx is, I think it's maybe 3, 3. Let's say 3. Too far. 3, 1. So we have 4. So 3, 1, probably here. I think we haven't yet drawn. Let me draw first. Let me run that. So maybe it's going to be like that. Okay. So this is our approximation to help out analytically draw the solutions out of the direction field. So direction fields will help to give some directions to our solution. So our solutions, it depends on in which initial condition they will be. Okay, I hope you get my idea. But perhaps the better way to look at this is if we take our graphing calculator. So let me prepare the calculator first. Okay, let me stop the sharing for a while. And give you my second screen. Okay, now you'll see this is the idea. Okay, let me make it bigger. Okay, if you see my screen, this is y plus x that we have drawn before. It's more accurate because it's using graphing calculators, in which you can find in GeoGebra. I will share later the links and how to use it. So we can define our functions here, our differential equation. This is f prime xy equal y plus x. So if we are, it's actually giving you 4 solutions. So the person who creating this is another professor, giving you 4 solutions that you can play around. So let's say we take the solution A, okay? So if you can see here, of course, we have the line here in which it is representing the slope that is going to be equaling -1, right? And if we try to play a little bit, if we take this around here, it's going to be, so the solution here, maybe if we give another solution, maybe over there. So if we change the initial conditions, the solution also change, right? It's going up, like that. And maybe giving you another solutions that we have. Okay, so see that it will brings you to, and if you want to make it more, for example, you can change the density and the length of the slope. So if you want to make it smaller, you can do that as well. But I think better to have some sort of line there, because remember, the slope is approximations, right? Approximations of our curve. If you remember the calculus that we have, how to use approximation, especially linear approximation in calculus, in which that is the how to approximate the curve through line equation or the tangent line. And we can also make the density, how much we want from each point. Like, for example, this one is having in between, like maybe 2.5, 1.5, it has the slope. Or if you want to make it more like maybe here, density, you can try to play around with this as well. But I think the general idea, I believe you can take it as you may have slope fields to help you to draw uh, the solutions. Okay, to draw the solution curve. Okay, and how we can draw and how the reaction that we have, it will be also considered in the later sections when we deal with the autonomous differential equation and the attractor and repeller. I will explain later. It seems very technical. The word's very technical, but it's the function is actually easy. Okay, so let me stop sharing, or maybe we try to take different functions. Okay, maybe x. Um, let's say x plus y, y, um, maybe x plus y, or not x plus y, maybe y minus 2x. Okay, it's another functions, and maybe 1 minus xy. Okay, again, different functions. Let me check if we can make it into our functions. Sin y. Okay, we can have sine also. Can we make squared? Let me check. Okay, y squared minus x, right? Okay, it's quite fun. We'll give you the links later. Okay. So let me stop sharing and go back to our notes. Okay, I hope you get the idea behind the slope fields. Okay. Okay. Okay, if you look on your textbook, you may have seen this is 0.2 xy, okay, the differential equation, which means that we can predict our solution curve and just take some maybe here. Oh, it's going to be like that. Maybe make it more bold. Maybe that, or maybe going around here, as you can see from this one. Okay, this is a prediction. So probably that is how we approximate the solution curve of uh, using the direction field or slope field. Okay, let me check what part that I missed. Oh yeah, Sam, yeah, do you want to ask? The curve represent differential. No, the which the curve represent the solution. You mean the constant from where? Okay, you got it. So which means that let me erase this. So what I mean in this equation here, this is the DE. So instead of looking on how we can solve this, we can use this as the slope. Okay, so we can take, well, for example, we can take 0, 0, for example. dy dx is equal to 0, right? If we see from here, it's 0 like that. Okay, and of course, in all x equals 0, they are all horizontal. The gradient is horizontal, right? and then maybe we take some different point, maybe 1 0. Oh, not 1 0, maybe 1 1, because it's also 0, it's also horizontal, maybe 1 1. So dy dx is 2 over 10 or 1 over 5. So that is what we have here, actually. It's around 1 over 5. Um, it's difficult to draw in hand. Yes, different solution to the DE. Yes, all the curve represent all the solutions that might happen. Okay, we call that solution curves that might happen. So, for example, if we take 1, 1 here, like this is 1, 1, right? This is 1, 1. So, probably the solution, if we look here, is that arrow, and this is horizontal, probably this will have that kind of curve. My curve is so bad, sorry. Yeah, that kind of curve. Or maybe if we take this, maybe this is one of the solutions, okay? So I think you can check with the graphing calculator. I think that would be better. But sometimes uh, in exercise, you need to use your intuition and draw and sketch with your hand. That is, I think, good for um, learning how to improve your intuitions in graph, okay, in math. Okay. Okay, like this example, I think this is this sign that we have. Let me check. Okay, oh, this is the, let me put this into here. So this is dy dx sine y, okay? And initial value is when y is 0, and when x is 0, y is negative 3 over 2. And this is this blue line is the solution curve that is contains this initial condition. So initial conditions start from 0 here. This is negative 3 over 2. It's around here. It's going down like that. So sine is going to be decreasing like that. And yeah, if you see, uh, there are some parts of our curve that is not really defined. It works like an asymptote. Okay, if you see from my picture here, that line here, this is of course when it is the gradient is 0, for when dy dx is 0. Of course, this is when sine y is 0, so y is 0, right? And also this, right? This asymptotically behavior will be, we can consider later um, as our, we call that um, the attractor or repeller. Okay, increasing, decreasing when you move the point, how the curve will be. Okay, so that is the slope fields. Okay, this is just to show you. We have some asymptote here that we will learn more about this asymptote in the next section, in which we are going to discuss. It's called the autonomous first order DE or differential equation. Okay. But maybe before that, I think I prepare. Oh, let me check. I prepare the one. maybe let me start with this one first. Okay, I think this is fun, I think, and we can check. Okay, so we can check 1 minus xy, and we have 4 initial conditions. Let me just give you this one example, and then uh, we can continue to the next section. Okay. Okay, the first initial condition is 0, 0. If we check, the 0, 0 is going to be this line here, right? So what is your suggestion? My suggestion is, because if you move x going to the right, if you follow the arrow, it's going to be here, and the previous one is going to be here, right? So probably this will be going over there, or maybe it's not really smooth, but you can see it's going to be over like that, and this will be, yeah, yeah, I think it's possible. Or you can draw this in the graphing calculators and check the solution curve. I think that will be better approximations rather than our hands, because our hands usually doesn't really accurate, right? That's the first one. Okay. The second one, y2 2, so x equal to y equal to. So maybe this is 2. This is 2. We can check. It should be 1 minus 4. It should be minus 3. Oh, 2 is here. I didn't see. Okay, this is 2, 2. 2, 2 is here. So 2, 2 is going to be here. I think this one, right? And from what we have, because it doesn't really give the whole section of the graph, so probably, let me write with blue. So maybe it's going to be, okay, one part going there. And I believe that this is supposed to be having another one here. So, but let me just say that that is one way to look at. And the other one, negative 1, 0. Negative 1, 0 is going to be here. Let me change the color again. Negative 1 here. And negative 1, 0. Okay, negative 1, 0 is here. So this is supposed to be similar. It's going to be looking like this, but it's going to be here. And it goes up and down. I think that is our approximation, right? So as long as it's going to be looks like the same, looks similar, I think that's still okay. Another one is 0, 4. So 0, negative 4. So 0, negative 4 is going to be here. So that is, I think this is going to be going over there, over there, over there, and going to be there. Or maybe I think it's more clear if I take the glow. and this. Okay, maybe I'll like that. Okay, and that's the solutions that is asked by this four initial conditions. Okay, so if you are given kind of slope fields, then that's what it is. And uh, probably how to sketch is not going to be in my quiz or the exam, but how the fields works, maybe that will be the question. Okay, and maybe just giving you whether verification or confirmation whether that's true or not. Okay, so maybe that's it. But I hope you can get some sense on sketching. Okay. Okay, I think this one you can try by your own. I think later on. Okay, now we move to the next section, which is the autonomous first order differential equations. Okay. So what is autonomous means? So let me give you a phrase that is uh, differential equations that is free of the independent variable. We know that we have linear, nonlinear, right? Now we can also define the first order can be autonomous or not. Okay. So an ordinary differential equations in which the independent variable does not appear explicitly is said to be autonomous. Okay. So what is independent variable? Which means that if we have, let's say, y is function of x, then x is our independent, right? Independent variable. Y is our dependent. So what the differential equations here means, the autonomous means is, for example, if you just have uh, dy over dx is 1 plus y squared. This is autonomous because the x is not explicitly appear in the equation. But if we have like the equation from the previous questions, like 0.2xy, we see that this having x. This is non-autonomous. Okay. Okay, and then in autonomous, we may have the general terms. Okay, to make it uh, easy to be think, we can think the general form for this dy dx, okay, as function of y. So it's only consists of y. But of course, y is actually a function of x, actually. But we can write in differential that is the dy dx is a function of y. Okay. Let me just give you what does it mean. Okay. Before, if you look in the textbooks, maybe it's a little bit complicated with some technical words, but let me just explain it easily for you. Okay. This is later on. Maybe going here. All right. Let me just make the idea, or maybe let me just go through, because this is important. Let me just go through one slide before to give you an idea of autonomous. Okay. So if you have, for example, just give you an idea example. We have 1 plus y. We have 1 minus y. Okay, this is autonomous. It's a differential equation, linear, and having the function of y. Okay, it doesn't have any explicitly x, right? Okay, now if we remember uh, in calculus, especially calculus 1, when our functions first derivative is, if the first derivative is 0, then we are going to have our critical numbers, right? Critical numbers or critical points. Okay. Now, similar in autonomous, we will have a critical point. So when the dy dx is 0, then as implications, then we may have 1 plus y 0 or 1 minus y 0. Okay, so we may take the y equal -1 and y equal 1. This is, we can call also the critical points, or in a sense of our autonomous, we call this uh, equilibrium solutions. Okay, now perhaps to make it um, easy, let me go through. Let me stop this sharing. Let me just give you an idea first. Stop the sharing first. Okay. And let me give you the other screen. Okay. Now let me erase the solution and let me change the graph is 1 plus y, or maybe 1 plus y and 1 minus y. Okay, that's okay. Now see that in y equal 1, it doesn't have anything, and in -1, it doesn't have anything, because when we have y equal 1 or -1, that is our equilibrium, right? Or our critical points or our equilibrium solutions. What is the implication? Okay. Now the implications are, when we move this, okay, let's see. We have at the -1, it's we have we have a line like that. If we increase, maybe if we just take this in between 1 and -1. If we take this point going up, and up, you see that this line here it goes here, right? It goes here. And if you take down, it will goes down there. Okay. Okay. Now, if we are, let me take this as a screenshot. Okay. Wait for a moment. Let me just take the screenshot into my notes. Okay. Okay, let me stop sharing. Okay, let me share another my notes again. Okay. Okay, now let me go through what we have here. Okay. Okay. We may have a new terms. Okay. So let me draw that we have an asymptote here. That is, or maybe it's two both, maybe going a little bit thinner. Okay, that is y equal 1 and y equal -1 here. Okay, let's say this is our asymptote. So this is y equal 1, this is y equal -1. Okay. Okay. At y equal 1 and at y equal -1, we call this, it's asymptotically stable. What I mean is the curve itself, it's stable. It doesn't go anywhere, right? It just stays as it is. So if we increase x from the right, at certain point, it doesn't crossing this asymptote, right? So we say that it's asymptotically stable. So an equilibrium solution, y equal, let's say, a constant a, is asymptotically stable if solutions that start near a tend towards a as x going to be infinity. As we move the x from left to right, we are going to see that it is going to be just make it into the asymptote. The name is asymptote, right? So it doesn't go anywhere. It is stay besides the asymptote as we increase x. Okay, that's we mean we are going to define that as a stable. And equilibrium solution y equal A is asymptotically unstable. Let me make unstable. Let me make also this with green. So unstable if solutions that start near A leave A as x increasing, which means when we have maybe going here, we move, and somehow it's going there. It leaves, if this is A, and it's going to be driving away from A. So we call that unstable. Okay, to make some notes on how we make this into our observations, we call, or we are using what we call the phase portrait. And we can denote this as our critical points. This is 1, this is -1. Okay, now we write our differentials. Okay, we are having, let's say we are going to, let me erase a little bit here. Let me just take notion at between area or interval between -1 and 1. If we take, for example, 0 in our y equals 0 here, it's going to be positive, right? It's going to be positive. So when we have a positive, we make an arrow that is going to be towards upside, okay? And when we have maybe area here, let's say we have 2, this will be a negative, right? Negative. We make this going down like that, okay? And now, when we have a negative, let's say -2, we are also, let's say this is negative, this is -2, so it's become positive, positive, negative, it's negative. So it's going to be down here. Now this is related to what we call next is attractor and repeller. Now we may say that this stable equilibrium, because it goes from up to down and down from here. So it's stable equilibrium. But here it's going away, it's going away. It's unstable. Okay? As we see from our graph here. So we may see that this is not this, just this equal 1, sorry. It's asymptotically stable, where the other one is unstable. Because if we look another way, let's say from here, it's going to move through A, right? Or maybe going there. Okay. Okay. Now that's just the idea. Okay, the idea for stable, unstable. Okay. Okay, now let's see in more general equations that what is the autonomous means, or what is the phase portrait, the stable, unstable, equilibria, what does that mean? Okay, move to here. Okay, let me move. We move this to the part. Okay, let me move again here. Okay, consider we have this differential equations, which is we have P, okay, as our variable, and A, B is our constant. So P is our dependent. Oh, let me write in green. I think doing this better. P is dependent variable. T is independent. Okay? And A and B, they both positive constant. So the general terms for this is the general DE is a function of P. Okay. So of course this is going to be autonomous. Okay, let's see whether we can make out our critical points from here, from the equations, and make out the equilibria solution. Okay. Okay, so P A minus BP is equal 0. So we are going to see that the conclusion from here, it seems that the critical point is when P is equal 0 and when A minus BP is equal 0, or P is equal A over B, right? Yeah, P A over B. So we are going to make out our phase portrait based on what we have. Since A over B is a positive constant, so A over B is over here, 0 is over here. Okay. We can see this from the let's say the interval from negative infinity and 0. So if we imagine maybe negative 1, if we imagine through our points here, what will happen? So this will be a negative. Negative 1 is becomes plus, so it's positive. So it's negative, right? So it's negative. So we can say that p functions t is decreasing, right? And we are going to draw the arrow going downwards like this. Okay. And let's say we are going to have a over b to infinity. So since it's irrational, then we are going to see that this goes to be also decreasing. Okay, because this is positive, right? A over B, and this is A over B. This uh, A over B positive. Maybe we have 2, 3, so we can just take some numbers over, and this will be a negative value. Okay. So at AB infinity, this is also decreasing. But when we have 0, AB in between, well, we might have maybe um, since it's a fraction, then this will be going to be increasing. So this going to be oh, I think we can take short break. Okay, I need to recharge my Apple Pencil. So I think we can have a short break, uh, 5 to 7 minutes. Okay, so we are going to continue at I think 2:35. Okay, hope you don't mind. So okay,
Uh,
you-
Professor, I have
yes.
a question.
Mm-hmm.
Do this kind of like prediction using the
Mm-hmm.
slope field always work like completely? How precise is it? Like how precise?
Yeah, it will always work as long as it is autonomous first order differential equation.
And the idea of repel and this one too.
Yeah, yeah,
Okay,
yeah.
thank you.
Okay. So we will have a short break. Okay, see you later. Okay. Oh, Doron, you asking? No sound? Oh yeah, we have short break before one. Okay, we are back. Let me check my pencils. Okay, I think it's okay. We are going to look at uh, this. We call it. This is the face portrait or face line. So we are going to see whether the uh, the arrow going up or going down, and it will be determine. It will determine what we call attractor or repeller. Later, I will go in detail. But let's just observe in subset of regions that we have in this particular example. Okay. Okay. Let me go through. Let me check. Okay. Okay. This is the face portrait and solutions for each curves. And if we are looking, what we have is actually similar to uh, the, 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 the picture that we have seen in the graphs, like in this the slope field, like 1 plus y, 1 minus y, right? Now, let's construct this, or let's break down the region, okay? So let's say we have the region 1, 1, 2, 3. The region 1 is from negative infinity to 0, and region 2 is 0 to a over b, and region 3 is from a over b to infinity. Okay, and don't forget we need to define also the t that is everywhere, right? So the phase portrait tells us that we will have a decreasing pt, decreasing here and here, and increasing pt in between 0 and a over b. Okay, so okay, so let me make some notes. For p0 less than 0, p0 means that initial, we have the initial value. So let me write here, if p0 is p naught, this is initial value. So then, okay, then for initial value less than 0, the functions or the pt is bounded above. And pt decrease without bound. As the increase. Okay, so pt is goes to be 0 as t is goes to negative infinity. Okay, so it means that if we take this to here, it will be close by this 0, right? Okay, that's what it means. Okay. So which means the t-axis the graph of equilibrium solution Pt equals 0 is horizontal asymptote for the solution curve. Okay, this is just what we have. Okay, so basically, I think if you understand through picture, through visuals, through graph, I think that's okay. Okay? This is just what we have in definition. So let me go back here. What we have here is actually like we have in when we play around the graph in the slope fields before. So when we move out this point, okay, we are having different behavior. So we are going to have like as t increase, it will be going to decreasing without bound. So it's going to be negative infinity, right? It's going to negatively large, okay, all the time. But when we are going to move this to t negative infinity going here, it will be going to be zeros. It's bounded above here. It's bounded above. Okay. This is what does that mean? And for um, for the area between 0 and a over b, pt is increasing, right? Pt increasing. So pt is going to be as large as a over b as t is goes to be infinity, and pt is going to be 0 as t is going to be negative infinity. So the graphs the graphs so we have two horizontal lines. So the graph of two equilibrium solution pt equals 0 and pt equal a over b are horizontal asymptotes, okay, for any solution in between these two asymptotes. So in between here, this area in between these two asymptotes, the solution curve must be in between these two equilibrium solutions. So you can, if you maybe draw, move around the point. Okay. Let's say we move the point here. This will be having the same similar behavior. We move here, it's having the same similar behavior. Okay. And for the last part, when we have the initial value of p0 greater than a over b, then pt is bounded below. Which means bounded to the asymptote a over b from here. This a over b is bounded in this asymptote. Okay. Since pt decreasing, then pt goes to a over b as t going to be infinity, and the graph of equilibrium solution pt equal a over b is horizontal asymptote for the solution curve. Okay. Okay. Okay, the next thing is uh, what we call the um, attractors and repellers. But before that, let me go through some intro. Okay. Okay, let's go to this part. So attractors and repellers. So when we have, for example, we have the defining our critical point C, as we see from here, we define, and nearby the C, probably we will have our initial value, and we know that it's already set, the arrow already set. Okay. If the arrow goes like the one is going there, one is going there, is going to be closer to each other, we call this an attractor. Okay. Attractor. Okay. So this is called attractor. Attractor. And if both are driving away from each other, so this goes up, it goes down, and driving away, then this is repeller. So attractor, repeller, and if both goes up or both goes down, this too is called the same semi-stable. Okay, that's the attractors and repeller. Of course, that attractor will contribute that this will be a stable, asymptotically stable, that I mentioned before. A repeller, of course, this will contribute to the unstable, okay, unstable one. And aside from the attractors and repeller, one thing to mention that is, I think, to notice is for autonomous differential equations, if you see the elements, let's say we see this slope field, okay, the, the the horizontal line, they are all the same slopes, right? The same slope, okay. And in the vertical line, it's vary. I think that it's intuitively you can also predict because we are only looking at the function of y, in which the only way that the slope can be varied is if we have a different slope in y-axis, right? Okay, but in the horizontal they will be the same because we don't explicitly um, put the independent variables in the functions, right? Okay, okay, that is the so this is actually what you can tell about the autonomous differential equation. So autonomous differential equation, when you have the independent variable is not appear, and when you see the slope fields, you see that it's vary only the y-axis. Then you can definitely tell that okay, this is autonomous. Okay? Autonomous differential equation. Okay. Okay, perhaps before we move on, uh, let me just take a look on this differential equation here. Okay, we have two differential equations. So first, the left one here, second one in the right hand. So when we solve this, it seems that it goes to be a similar solutions, but when you check the solution curve and you check the these two initial value, you will get the solutions that is going to be y equal x 1 minus. So if you want to define it clearly, you need to define this in terms of we can see that from here the critical point is y equal 1, in which we can see later the asymptote. And you will see that the difference here, plus half, minus half, it came from the initial conditions. Initial conditions. So of course, the initial condition stated that the solution can be our solution that have existence and uniqueness when we think about the interval as we mentioned before. So if this is having 1, then we need to make sure that this is uh, not equal 1, right? And at the x. And when we draw the curve, let me make it a little bit smaller. So when we draw the curve, we see that this is example for semi-stable. We see that the when we check the one here, when we check with 2, we check with 0, we check the solution here, they are having the square, right? So of course it goes to be positive. So both sides is going to be positive. So it goes to be going up. The arrow is going up. Okay, the arrow is going up. So it's increasing. It is also increasing. So what's happened in the graph? Okay, what happened in the graph? If you graph this with this solution here, if you graph, then of course this going up, right? It's correct, and also this is going up. But the difference is, uh, when you're going up from the bottom here, you're going to have our asymptote here, so it's going to be there, and eventually, uh, because we have some restriction on the interval for x, then our x minus negative half, this becomes our asymptote. And similarly, you will see that this is also happen, but it has the same phase portrait. So it goes up, increasing. But of course, we have the asymptote for x and asymptote for y. Okay. So this is y0 less than 1, y0 greater 1. This from the initial condition here. Initial condition. So the solution is actually the blue color one. Okay, the blue color one. This is the predictions, but because of the initial value that we have, 0, -1, 0, -1, and 0, 2, and the blue one is the solution curve. Okay. Okay, attractors, repellers. What else do we have? Oh, another one, the last one for this part is the translation property. So because the autonomous in horizontal is just as it doesn't vary, then we can shift it uh, in the horizontal shift in the horizontal axis easily, okay? Because it will be the same curve, okay? So if y of x is a solution of autonomous differential equations, that is probably dy over dx equal f of y, then we can shift it and we can make x minus k where k is constant. So this is also a solution. Okay. Okay. Uh, by the way, please check the chat box. I send you the Google Forms. Okay. That is, I think I can make it for attendance, and uh, probably I need your email, okay? Because sometimes I will give the results for quiz or for the midterm or for the final through email, and sometimes if you are using the email from university, sometimes it's not really smooth. Okay? It's not really smooth. So um, you may choose if you want to use the university email. Well, the downside is maybe it's not as smooth as other server like Google or maybe Yahoo. Probably you have Gmail, right? So that is better choice to set up the email, and I can also use the email for sending you some either homework, exams, or anything sort of that. You can fill the information later. That's okay. Okay. And I can also adjust that as our attendance for today for this session. Okay. Now the next part on our course today. So we finished the slope field, um, autonomous differential equation. At least you know the visuals, what it means. Some terms that is technically maybe some of you still not really familiar, like the asymptotically stable attractors, repellers. Okay, I think if you understand the visuals with the graphs, and maybe you can just go to this, go to the slope field and draw and move around. I think that's will be better. Okay. I think I can give you the link for the slope field. Okay. Let me write in the chat box, and so you can play around with the slope field. Okay. So if you click the slope field, you will get the. It's a little bit different from what you see before, but it's the same. Actually, the same. You can just type in any equations. You can change the how it looks like, the density, the length of the slope. You can change and you can adjust, and you can click the solutions, and you can track the point for the initial condition that you would like to see. Okay. I think that's better rather than just writing and then, because sometimes when you learn more and more advanced mathematics, the graph is not easy to be drawn. If you remember how to draw the double integral, the triple integral, it's already complicated. Later we will have the same fields like slope fields, but imagine if it is in 3 dimensions. It's really hard to imagine and to draw. So I think having this some software that is easy to be compute and rearrange, it's very useful. Okay. And it doesn't need many technical writing codes, like for example, like coding, or maybe using like MATLAB if you somehow using that works or research. It's good, but it takes time to learn, right? Or if you are familiar with LaTeX for coding, usually I write LaTeX for my exam, so to be able to be compute in some softwares. So I think you can also learn that as well. Okay. I think in the future you will it will be useful. Okay. Now let's go back to to what we have. Okay, so we have learned the slope field, autonomous differential equation. Now we are going to be more talking about the method. Right? So the first method in the first order equation we call the separable equation. Let me write the equation here. Okay. So the method we call the separable equations. Okay, recall that when you have, let's say, y prime equal f of x, or um, dy dx equal f of x, we can just integrate this, right? And you learn integrate in the calculus. So typically, we can just integrate. So what we are going to write in integrations is, let me draw here. So integrate with respect to dx, with respect to dx. Okay, that's how we are going to integrate. Technically, that's how we are going to do that. So y is integrations of f of x dx, and it will resulting a plus c from the other side. Okay. But this method, it works for any y prime equal function of x. But in the general form, like y prime equal function of xy, it will not work because we have y, right? If we just have x, it's okay, it's happy, right? But if we have y, then how do we integrate this with respect to x, with respect to y? How do we integrate it? So,
Sure.
Dave, you want to ask?
No, Professor.
Oh no, okay, okay. If we try to still conduct the integrations, then this will yield that this f(x,y), let's say the x plus c. But the question is, what is this? If you have this fx dx, we can use our methods in calculus 1, right? But how about this? We have xy dx. Okay. Now the problem is on one way y. Okay. Okay. So the problem can be solved through what we call the separable. Okay. Let's say we are going to have y prime is f of x and g of y. So we have two functions. Okay. So function of x. So functions of x and function of y. Okay. So if you write in, let's say we write in dy dx equal f of x g of y. Okay. If we rewrite this, okay, we move dy and g of y becomes here, and we are going to have f of x and dx. Both sides it looks like something that we can integrate. So take the integrations. So the left part is integration with respect to y, and the right side is with respect to x. So perhaps this can be solved. Okay. Now take the example. Let's have an example. So let's say we have dy dx equal xy. I think easily enough that it's easy to be going to be separated. Okay. Of course, if you see and just try an error, you will see that y equals 0 is also solutions, right? Okay. Let's say we assume first, okay, that y should not be 0. This is just assumption first, okay. Why I need to write this? Because I will have 1 over y dy and x dx, okay. And of course, y cannot be 0, right? So take the integrations, both sides. 1 over y is ln, absolute value y. Don't forget absolute value, okay? X squared over 2 plus a constant. Okay? Now let's assume that this y is going to be e x squared over 2 plus c, and we can write this as x squared over 2, and then E with C, and it is another constant that we can write, let's say D. Okay, let's say D E x squared over 2. So this is our solution where D is a positive constant, and because we can also write, then the conclusions is, let me write, over here. Okay. So because of the absolute value, we now can write, and then because D is positive and E is always positive, so we can just write D E x squared over 2. It's our probably our solutions for any number D, right? Now, as easy as it gets, what we need now is we can check. We check d over dx is, so chain rule, x squared over 2, it's become 2x over 2, it's x. So x d e x squared over 2. And what is x squared over d x squared over 2? This is just y, right? This is y, so xy. So, okay, it's true that this is our solution, okay? So for some sort of confirmations, you can just turn back to differential equation by differentiating the solutions. I think differentiations is basically a little bit more, I think, simpler than integration, right? So I think not a big deal to check, okay? Okay, let me check what else that is going to be in our. Okay, so for, by the way, for the Moodle, I think we need to wait until Friday. I'm not sure when I can use the Moodle. Before before this week, there will be no assignment or homework. I think that is okay. Okay. Uh, okay. Okay, let me go through another example. Okay, so let's consider Okay. Now, if you want to solve this, solve the DE. Okay. It seems that I think we can separate, right? We can separate y. We can separate x, right? So perhaps this will be y squared plus 1 over y dy and equal x dx. And then take the integrations. I think we can solve this y plus 1 over y. Okay, I think better that way. So this will become y squared over 2 plus ln y, and then s squared over 2 plus a constant here. Or maybe if we try to mix up the y squared, we multiply with 2. So we have x squared. Maybe it's c1 is c2, okay? And sometimes it's not easy if you want to make the solution in terms of y, okay? So if we would like to make y equals some equations from here, because we have y squared and ln y, it's not easy, right? So what we can do, we just live at it, okay? And we call this implicit solution, as we discussed at the beginning, okay, in the beginning of our class. Implicit solution. What implicit mean is we don't really directly see y equals something, but we are going to see maybe y squared, blah blah blah, okay, or maybe y cubed, blah blah blah, okay. Because it's not easy to make it into an explicit solution. Of course, if you want to check the solutions, then we can find the solution through differential. We can implicitly differentiate. Okay? We can implicitly differentiate. So, for example, we can differentiate so the whole thing. We differentiate with respect to x. This is assuming that y is function of x. So we will have 2y dy dx plus 2 over y dy dx is equal to x. So 2 dy dx, we can cancel all 2. This is y plus 1 over y for x. So we can have dy dx. We can have this is become y squared plus y plus 1 over y, right? So dy dx is equal x y squared plus 1, and it's going to be correct, right? Or aside from using this, we can also use the graph to check. And if you look this differential equations and if we check and try, for example, y equals 0, I think this will be also a solution, right? This kind of solutions, sometimes we call this a singular solution. So the general solution is this, okay, this, or maybe here, and also and y equals 0. Y equals 0 is frequently can be a solutions for uh, some equation, and we usually call this type of solutions a singular solution. It's not really in our calculation, but when we check, it's going to be true also. Okay, let me give you another example. Let me check. I think I missed out something. Okay, this singular solutions, I think I can explain in more with the context. Okay, what we are going to look at is uh, we may have some concept of losing a solutions in which it's related to singular solution. So when we are having our separating variables, we separate, and then let me write here, since the divisor variables could be 0, okay? So specifically, if we, let's say r is a 0 of the function, let's say g of y, and substitute sub the y equal r into dy over dx equal f of x g of y. And when we sub this y equal r, this makes both sides 0. In other words, that y equal r is a constant solution of differential equations. But after separating variables, probably what we have, so after separating variables, so after separations, dy over g of y is equal f of x dx is undefined at r. So as a consequence, y equal r may not appear as a solution. Okay. So this is what we call the losing solution. What it means is uh, if we directly go through separating variables directly without thinking about the function itself, then when we see this, oh, it's undefined at some point at r. So we skip that r at all. And then we lose, the consequence is we lose y equal r as a solution. Okay, this type of solution, we call this is singular solution. Okay, because this type of solution is not show up in the family of solution after the integral. Okay, I hope this can be understandable. Okay, so what the idea is, okay, when we have here, okay, if we not think through and we are thinking, okay, y is positive, right? So it should not be having any zero, right? So y equals 0 is not solutions if we just look at this end result. But if we look at the very beginning, of our differential equations, 0 is okay, right? So y equals 0 is a solution. But when we separate the integrations, we may lose this solution. So this is really important. Okay, so if you not think through from the beginning, then you might losing this y equals 0 as a solution. Okay, so the total solutions, so the general solution is this and this. Okay, this is what I'm trying to say. Okay, so if you directly goes to separation and you see that when you separate, oh, it will be undefined at some point, and you will ignore that point, ignore the equation. Whereas the equation is actually a solution, but you ignore it, so you lose a solution. So that's losing a solution mean. Okay, let me go and see uh, what we are going to have in the as example. Okay. So any solutions that cannot be obtained from the family solution that we have is called a singular solution. Okay, let me give you another example, also for reviewing some calculus techniques. Okay, I hope you don't mind to reviewing some calculus part. Okay, let's say we have dy over dx equal y squared minus 4. Okay. Okay. If you want to solve this, we can go through some separations. Let me just go through separation first, and we can observe, okay, what we need to do here. Okay, let's solve this. So dy y squared minus 4 and then dx. Of course, this will be integrated, right? And how to integrate the left side? This is what we call a partial fractions. Okay, so if we factorize, this becomes this, right? Let me just write this first. Okay, so let me write 1 over y squared minus 4. This will be y plus 2 and plus y minus 2. And just let me just give you a constant. Okay, this partial fraction is also one of the methods that will appear quite often, especially in Laplace. So when we later learn about Laplace, we will have some sort of techniques to solve that requires partial fractions. So I hope you can review this partial fractions. Okay. Okay. Now we need to find the constant a and b. How to find that? First, we just need to equaling both sides. So this is y plus 2. So y squared minus 4 divided with y plus 2 is y minus 2. Multiplied by a, that is our first step. And then plus, this will be y plus 2 multiplied with b. And this should be equal to 1. We need to equaling this, right? Okay, now take this ay minus 2a plus by plus 2b equal 1. And then grouping all the variables, a plus b y and minus 2a plus 2b equal 1. And definitely we can see that minus 2a plus 2b is equal to 1. A plus b is equal 0. Okay, equaling both sides. Okay, now okay, we can multiply with 2 with 2, right? So let's just take minus or maybe plus to make 4b is 1. So b is 1 over 4 and a is negative 1 over 4. Okay, so we can transfer this into our solutions. That is integrations. A is negative. So let me write b first. So b is positive. Y minus 2 minus 1 over 4 y plus 2 dy. The integral dx. Okay, now integrations here, because we already have using the partial fraction to separate each of the integration, then we can write this as 1 over 4 ln y minus 2 minus 1 over 4 ln y plus 2. Right, and then this will be x plus, let's say, the constant 1. Okay, multiply by 4, we have ln y minus 2 minus ln y plus 2 equal 4x plus, let's say C2. C2 is 4C1, right? Okay, still okay. And then ln is y minus 2 defined by y plus 2 from the logarithm. So 4x plus c2. Or we can get and removing the ln with the exponential. Okay. Okay, now if we try to solve this, so y minus 2 is y plus 2. Let's say c2 is c3. So y y e for x c3 plus 2e for x c3. Okay, goes through here. So y 1 minus e for x c3 is equal to e for x c3. So y okay. Oh, plus 2. Forget plus 2 here. Plus 2. Okay. So 2, 1 plus e for x c3 divided by 1 minus e for x c3. Okay. Okay. This is our plausible solutions. But remember, okay, if we check, we know that we have this DE. Okay, so if we check this, okay, we know that this is our result of factorizations. Then this y equal 2 and y equal negative 2 are to our equilibrium, okay, if we remember the phase portrait. So this is our equilibrium solution. And the solution y equal 2, so this y equal 2, if we look at what we have here, is we can write y equal 2 is a member of family solutions. That is y equal to 1 plus e for x c3 divided 1 minus e for x c3, right? It's a member of the family solutions, okay? Because E is a constant, right? However, okay, however, y equal -2 is a singular solution. From here, from the factorizations, okay? But let me write here. Y equal -2 cannot be obtained from family solutions, right? Which is this whole equation here. It's a solution, but it cannot be a -2, right? So if we directly integrating this and we have a conclusion that this is our final solution, only this part, then we will lose this. So we lose this solution. So this is a singular solution that might be lost, might be or lose if we directly compute separable integral. Okay, so first thing is check our always check the possibility of singular solution. Well, the singular things is actually similar with, if you heard the singularity in astrophysics, is actually the same or similar meaning to that part of finding the singular solution. But what I mean here is we may lose our solution, okay? One of our solutions. So we need to include plus minus 2 in our steps. Okay, any questions first? Okay, I hope you still remember partial fractions, some sort of that. Okay, hope you still remember the bottom part. This one, right? Okay. So far, is my writing clear, or maybe need to be more bigger or too small? Is it okay? This the first day. Okay. So in every attendance, I will ask some suggestions to improve. Okay. So I hope you can also give feedbacks, okay? Because I believe you guys have taken the course before, right? But I'm not sure whether my topics cover the same or maybe similar parts with other professors, because for this summer course, my topics is actually a little bit different if I compare with some professors. So I believe my coverage will consist of some basic parts on differential, some parts of factors, matrix, Laplace, okay, Laplace, and the factor calculus. Maybe we are not going to cover all of the sections, but the I think the big one need to be just covered. Okay, I think I think it's still fine. Okay, we give you more examples on what kind of questions that might be for the separable method. Okay, don't forget to write the Google forms that I sent in the chat box. Okay. Don't forget to write the Google forms. Especially if you have a feedbacks, please give to me your feedbacks. Maybe not clear my presentation, or maybe some suggestion. That's okay. Well, we still have time. Let me just go through some examples. Okay. Okay, we have cosine x and an e to 2y minus y, and we have dy over dx equal e power of y sine to x. We have initial value, y0 is equal 0. Okay, we can think first, check how to solve this. And I think we can solve by separable, right? Separable equations. We can separate y and x. So the idea is just separate a group of x and a group of y, integrate each part. Okay, that's easy to remember, right? The rest is you need some techniques in calculus, and of course, I cannot review all the techniques, but if we have time to have exercise, maybe I can have that as well. Check the initial value, find the constant, rewrite the equations. Don't forget whether you have a singular solution or not. Okay? Checking whether you have singular solution or not. If you have singular solution, you need to include that solution in the whole thing. Okay. And yeah, hopefully you can maximize or optimize your learning in the summer. And since the schedule is also, we have really tight schedule, so I need also to prepare some um, questions in for your exam or for your homework. So I think if we cannot cover all the topics, I think still okay. Still okay. Okay, maybe we can start with try to separate y and x. Okay, try to separate y and x. So first, we can take, let's say the left part will be y. So and the right side will be x. Okay, so we need to differentiate, integrate. Okay, so sine to x, we can have that as 2 sine x cos x. Okay, we can cancel the cosine. So we are left with 2 integration sine x dx. I think it's easy to integrate this minus cos sine x, right? But the left part, I think we need to still we need to solve it slowly. So this will be e y minus y e negative 1. So this will be dy integration. I think we can separate into two parts. So first is e y dy, and the other part is, okay, how to integrate this. Substitutions, I think no, it's not useful. We need to have integration by parts, right? Okay, I will give you tips to make your integration by parts quicker, fast. Okay. Remember, integration by parts is u dv equal u v minus v du, right? Okay, look what happened. Okay, so if you have any, if you define you define dv, so which means that you are going to integrate dv to find v, right? You are going to find u to make du. So you need to design u and dv from your equations, right? And look here, at the end of the process, you have another integrations. Well, actually, if you need this, maybe if you need to be integrated by parts again, then if you think this as again u dv again here, which means that we are going to have an iteration. So we are going to have another uv minus vdu again, right? We are having, we need to integrate by parts again. So I will show you there is some way to make it, to make this iterations in one table. Okay. So let me make table and write di. So d is for a component that you need to differentiate, and I is for integrations. Okay. So derivatives and integrations. Okay. Now let's say the component that we need to derive is u here from this one. It's u. The component that we need to integration is dv. Sorry. This become du. This becomes v by integration. Look on the signs. This is positive, this is negative, right? So what I want to make is a process. So let's say this is a positive and negative. So what we are going to do is we are going to multiply this positive with this and multiply with the diagonal here. And the last one, multiply here and writing here. So multiply. So this is actually integration by parts in a table. So we are going to have uv minus, and for the one that is horizontal, we need to make a integration and write vdu. Okay, let's apply this in our questions here. Okay. So we have integrations of y e negative y. Okay, and the more you are applying this, the more you know which part you need to integrate, which part you need to derive. Okay, so di, and let's say d is y. I will tell you why I choose y as our derivative after we finish here. And integration is e negative y. It's positive. Differentiate becomes 1. Differentiate becomes 0. And differentiate integrate becomes negative, and integrate once more becomes positive. So this is become this and this, and the last part, since it's 0, we can ignore that. So we can take this as negative e negative. Sorry, forget to write y. So negative y e negative y, and then minus, or here let's check. Okay, it's okay. Okay, this is our result. Okay, now the reason why I choose this y as our differentiations is because y will resulting in 0, and thus we will get directly the result. That's the reason. But sometimes there will be some times where the components maybe they will not resulting in 0. You can stop anywhere you want when that happens. For example, you have sine or you have e in which it's not going to be 0, right? So you can just stop it anywhere and just use that the last one. Okay. Okay. Anyway, let's solve this. So this part becomes, so let me jump here. So this will be e with power of y. This is negative and multiply with negative. So it's plus, right? Plus ye negative y plus e negative y equal, sign become negative, negative cos, so negative 2 cos x plus c. So initial conditions, y0 is 0. So y0 is 0. So we can apply 0 to all of the equations. So we will have so 2 so y equals 0, 0, 0, 1 plus 1 is 2. 2 plus 2 is 4, right? So 1 plus 0 plus 1 It's negative 2 plus C, right? C is 4. Okay. Now the initial solution, okay, so solution for initial value problem is e with power of y plus, let me just write as it is, negative 4 negative c cosine x. I think if we check, we don't have any singular solutions, right? We don't have. So that's the results. Okay. Okay. Any questions? Any questions? I hope my DI here can help you integrate integration by parts faster. I hope this can help you to take the integrations faster. Okay, I think I would just give you one more example and we can finish for class. Okay. And do you need time for taking notes, or I can give you one more sample? I think if you need the notes, I can give you the notes after we finish all the chapters, like chapter about ODE, the first order. I can sort all the notes and then give a PDF to you. Okay. Or do you want the PDF uh, per week, like every week? I can compile and give to you, or uh, based on the chapters. Maybe per week, right? Maybe per week. Okay. So you can refresh the contents every week, right? Okay. Okay. Let me go through example. Okay, one more example thing. Solve. So if I write like one here, it means that it's a prime. Okay, it's a prime. Maybe that, or maybe like that. Okay. 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 Let me just give you this question and try to solve for a while. Maybe if you have, if I give you maybe 5 minutes, if you get the answer, you want to chat, put the answer in the chat, okay, please do so. Just write the answer as if it is a complicated functions, then write the best as you can. Okay? If you want to write, for example, if I write this in terms of equation in when I write, then usually this can be write as or if you want to make it a bracket like that, that's also fine. This is how typically writing in in the notations. And usually the bracket will be helpful. If you want to write in some sort of coding, this can be write as fraction. Oh, DUI dx. If you want to write integral, yeah, integral step. So let me just wait for a couple minutes if you can try to find out what it is. Okay. 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 Please pay attention. Okay. So let me solve this. Okay. So x squared. Let me just write in terms of dy dx. Okay. And if you see this having x squared, right? And we have x squared and y squared. So what's happened if we treat this whole thing in the factorizations, okay? If you clearly see that we can factor out, actually, we can factor out 1 minus x squared and 1 plus y squared. So minus x squared becomes this one, okay? Plus y squared is this one, right? Okay. Now we can see clearly we can separate the groups, right? We can separate group of x and group of y. That's the idea. So x squared, or maybe let me write dy on the left. So maybe we can write 1 over 1 plus y squared dy, and then integrations, and we can separate this. It becomes 1 over x squared. Sorry, this is the x. And minus 1, right? So first, 1 over 1 plus y squared. Integrate with respect to y. What is that? That is our tangent inverse y. Okay? Don't forget that. And we can write tangent inverse as arctan if you want. No problem. And equal is integrations here. 1 over x squared is from negative 1 over x, right? And then negative x and then plus c. And we know that y1 is equal 0. So 0, so this is 0, and c is equal to. So therefore, the particular solutions that we seek or we are going to solve is we can write tangent inverse, and we can write y as tangent of negative 1 over x minus x plus 2. And this becomes our particular solution. Okay. Okay, I think we are going to end up until here. Okay. So see you on Friday. Okay. And don't forget to check the Google Forms. Okay? Check the Google Forms so that I can have your names in my attendance for this week. Okay. Any questions? Any questions before we close? Before I close the meeting? Okay. Okay, I think we are finished. So thank you for coming, and hopefully it can be useful, okay, and you can get a good result. Okay.